So as Sarah mentioned, the talk I'm going to give today is kind of a combination of some things I showed at GSA, but thank you for all those who had questions and comments for me at GSA. I've tried to correct all my sins from that time. So there are some updates, and then there's also a few bits on, on on tomography as well. Let's just get started. I think this is always a good place to start. And this is a global plate model showing what we know about Western North America in terms of the best constrained plate tectonic constraints, um, which are from seafloor spreading. So here in gray, you can see the uncertain and unconstrained areas and starting in the Jurassic. And at some point, you'll start to see the Pacific plate forming in the Central Pacific and growing. At this time in the mid-Cretaceous, there's still a significant gap. You can see North America moving. And then finally, we're getting into the mid-Cenozoic to the present day. And so this is really the challenge that is before us, is this massive uncertainty in reconstructing not just North America, but any area that has a lot of subduction going back in time. And so if we just kind of look at that in very practical terms, um, over the summer, some of us had a chance to go to Lopez Island in the state of Washington. We saw some nice exotic pillow lavas and pillow breccias that were probably of early Cretaceous age. And so if we try to put that as a pin on this map that we saw earlier back to 130 million years ago, there's an immense space that could be put into over 8,000 kilometers. And so those kind of challenges motivate us. Oh, sorry, before I go on. In today's talk, I'm going to talk a little bit about how we use tomography and slabs to fill in some of these gaps. But I'm also going to have a relook at the Shatsky and Hess conjugates that's abducted under Western North America, and then think a little bit about copper porphyry systems. And so I'm just going to close my door and leave it open. Seismic tomography is something that we have been trying to use to look for subducted tectonic plates, also known as slabs, and incorporate them into plate reconstructions. So this is an image from global seismic tomography. You can see that it goes from the surface down to the core mantle boundary at 2,900 kilometers depth. And for those who are less familiar with seismic tomography, what we're looking at are seismic wave speeds, in this case, P waves that are going through the mantle. And in faster wave speeds, shown here in purple, are these anomalies that have generally been interpreted as slabs. The resolution, importantly, is spatially variable, and it's very difficult to pin down the actual resolution. And it's no better than 100 kilometers scale, and probably a lot less than that. But over here, you can see where we have the presently subducting Cascadia slab. It does show up, at least part of it, as a fast seismic anomaly. We can also see the faster parts of the North American craton here. But how do we incorporate these types of constraints into plate tectonic reconstruction? Well, this is the kind of general philosophy that is guiding a number of us to approach this. And this is what I would call tomographic plate tectonic modeling. And here we're trying to extract slab information from the seismic tomography. And this is an example from East Asia, where again, we have very large gaps in the plate reconstruction shown here in gray. And if we're able to find a way to take a slab and bring that information back to the Earth's surface and estimate where subduction zones might be or the size of these slabs, we can then start to populate these uncertain areas with slabs. Now, in this case, this is a reconstruction again for East Asia, where there's many subduction zones. And here you can see all these colored polygons here have been populated. These are all slabs that have been reconstructed. And this is actually a movie. So if I play this over time, this is from the early Cenozoic to the present day. You can see that there's a lot of detail here. There's a lot of subduction of these slabs, and And I'm not going to go over all the different details, but the main point here is that if we're able to construct something from tomography to fill in these gaps that are in gray, it's very testable. There's magmatic histories here. There's a lot of subduction zones. There's paleolatitudes. There's collisions. There's all sorts of things. And now we can go into the rock record and test this model. And the reason why we take this approach is because all of the inputs for this model are redesigned to be tomographic. So they're from geophysics, and so we hold back the geology for testing afterwards. And so this plate model that you're seeing here is designed to, it's kind of scary, but it's designed to have minimal geologic input, maximizing the tomography, and then so that we can independently look at the geologic record. So I'm going to show you some examples of some philosophies that guide this and some results that we get. And at the end of the talk, I'm going to come back to this, and I'm going to propose a different way of working through this. And I'm going to call that a geologic plate tectonic model, which sounds kind of ironic because it should be geologic. But anyways, that's going to be one of my last slides. Now, how we reconstruct slabs is heavily influenced by how we think slabs are sinking in the mantle. So this is a great example of a very reasonable hypothesis. And the hypothesis is that if we think that there were subduction zones in the early Cretaceous and slabs are sinking, we can hypothesize that these slabs sink vertically, so that if we go to a present day snapshot, these slab walls here that are forming are basically sinking vertically into the mantle, and we can find them underneath the subduction zones where they formed in the past. So this is kind of the past, and this is the present, and I've put these together to show that basically these slab walls would just sink into and be deeper than where they were in the past. So this is a very reasonable way to see the mantle. And if we kind of look at how this influences how we might reconstruct a slab, so this is actually the only picture we have to work with. And this is the present day slab geometry. So we can imagine there's some slabs under North America. And so we would just basically reverse this process. And in some ways, you can think of this as taking a slab and floating it vertically upwards. So we go back to the early Cretaceous, these slabs would float upwards. North America, we know, is moving westwards, so we can bring it back to its position in the early Cretaceous, and we can try to reconstruct subduction zones and subduction polarities based on this. And there's been a lot of discussion on this, so I'm not going to go over the actual predictions here. But what I do want to say is that, again, this is a very reasonable way to see the world, that there's a lot of evidence, and there's mounting evidence for vertical slab sinking, for uniform rates of slab sinking in the lower mantle. This comes from things like global slab reconstructions, looking at geology and tomography together for every subduction zone that we know back to, I think it was maybe the Triassic or the Permian. And things seem to fit generally, vertical slab sinking. And also there's a number of geodynamic models that when we simulate this, the slabs do seem to sink vertically. But I want to present a different perspective, an alternative hypothesis. But first of all, going back to where slab sinking rates come from, this is really nice work done by Douwe van der Meer, using geology and tomography together to reconstruct the slabs that we see in the mantle from tomography. And here in this axis is depth. On this axis is the subducted slab age. And you can see there's this nice relationship with depth and subduction age that projects to around 1.2 centimeters per year. There is some, of course, there is some uncertainty, but generally things seem to fit at 1.2 centimeters a year. And then this is recent work from Yiwei Chen, who's a postdoc in Munich with Peter Bunga. And here we can see that if we run a global geodynamic model, and we can also reproduce generally a 1.2 centimeter a year sinking rate. This is depth again and age. And here you can see EWA using tracers, and it finds a distribution of sinking rates, but generally it falls within 1.2 centimeters a year. Now, importantly, this reconstruction is done in a spherical Earth, which is important with realistic subduction histories. But the thing is that if we look at this model that seems to confirm 1.2 centimeters a year vertical slab sinking, if we look at it in detail, and this is under North America, what we see is actually a different story. What we see is non-uniform and non-vertical slab sinking, specifically under North America. Now, what I'm saying here is that most parts of the Earth, as simulated by the geodynamic model, show vertical slab sinking, but not North America. And so here's the modeled mantle structure. This is shown in temperature. So there's some slabs that are formed that I'm not going to show it here, but they look similar to tomography. And what Yue has done in this work is he has put millions of tracers into the geodynamic model, so we can figure out what time and where these slabs were subducted. And so this is a picture here showing the same slab anomalies. And if we guess that these slabs that all at different depths or at the same depth were subducted at a certain time, this is the picture that we should see, that this is a hypothesized subduction age from tracers if slab sinking is constant. And so as we get deeper into the mantle, the color for the slab becomes darker, and that is because we were expecting an older age of subduction. But what these models actually show is something very different. This is the actual subduction age from tracers. And here in this red dashed line, you can see everything below this line was subducted before 100 million years ago, and everything above this line was subducted after 100 million years ago. So the sinking is non-uniform. And if we just calculate a mismatch between what we actually saw in the model and what we would hypothesize from vertical slab sinking, you can get mismatches up to 100 or even 150 million years of mismatches. So this is I'm not saying that this is actually what happens under North America, but this is what this geodynamic model is showing. And so this is something that needs to be considered. And not only is it this model that is showing this, but a 2023 paper from Legion Liu's group using a different code, but again, using a spherical Earth and realistic subduction histories, found non-uniform slab sinking. And both of these models, Yiwei's work and this work from Li et al. 2023, is showing that there's an area around the Circum-Pacific that seems to be showing non-uniform slab sinking, and that has to do with plumes, return flow to plumes in the Central Pacific. But all of that said, that it's worth, even though it's not the prevailing hypothesis, it's worth considering that slabs could sink non-vertically. And so this is a cartoon that I drew up to show the reconstruction method that we are using. Now, we didn't design this in this way, but we found that after publishing some papers with this method, that actually we are not making any assumptions of vertical slab sinking or slab sinking rate. So this helps to give an alternative viewpoint on North American plate reconstructions using tomography. So how does this work? Well, up here on the upper left would be a present day view of the mantle, for example, from tomography. And you can see this attached slab underneath North America, and there's a detached slab here in green. What we do is we consider the amount of slab that has been subducted, and we try to reconstruct this and bring this back up to the surface in one step. So here we're using the slab area. Sometimes we use the slab length. Depends on which part of the mantle the slab is in. And so by flattening this slab back to the Earth's surface, we get a certain length of slab. So basically, this is an area balance for the slab. We take it back to the surface in one step. And here we can see that as we unfold the slab, we have an overlap between this oceanic lithosphere that has been reconstructed and the North American continent. So what we're going to do is to play the plate reconstruction backwards in time and try to see what happens to this, what we call an unfolded slab. And here you can see the ages of the oceanic lithosphere has been reconstructed based on the existing ages in purple over here. Now going back to, so this is a present day snapshot with the unfolded slab. If we go back to 40 million years ago, so to do that, we bring this 40 here and 40 back together to the mid-ocean ridge. So we do seafloor unspreading. And then we bring North America back to its position at 40 million years ago. We can see that this unfolded slab is continuing to overlap with North America. So we continue this process of going backwards in time. And hypothetically, if we go back to 80 million years ago, and we take this 80 and 80 and put them back together at the seafloor spreading ridge, now what's left of our unfolded slab is no longer overlapping with North America. We now have a reconstruction gap. And at this time, we start to search in the mantle under this location for any reasonable slab that could fill the gap. And we find this green one under here, and we bring it into this gap. Now, sometimes it's vertical, sometimes it's non-vertical. But what we are doing is to fill in these gaps with deeper and deeper slabs. So this is an iterative reconstruction approach. The slabs are reconstructed one at a time, and we're working backwards from the known slabs, these youngest slabs, to older slabs. And so if we do this for North America, and this is some work that Spencer has done. Here you can see this Cascadia slab that is still attached to the Pacific. And here Spencer is taking the area and unfolding it back to the Earth's surface. If we put this together, this is the plate reconstruction that we get. Now this is in a moving hotspot reference frame and going back to paleomagnetic reference frame. And you can see the arrows showing plate motions. Seafloor ages here are shown by the different colors. I'm just going to play this. And the conclusion that we would reach is we would have two eastward subduction zones. We reconstruct the insular terrain here. In the mid-Cretaceous, it collides with North America, and it moves northwards and translates up to its present-day location. So I'm just going to play that one more time because we all have our own areas that we're interested in. Now, how should we understand this conclusion? I think that given some of the uncertainties in tomography, which I haven't fully talked about, it's really the style here that we're most interested in. Eastward subduction zones and a mid-Cretaceous collision. And so this is using this other way to reconstruct slabs leads to this type of hypothesis for North America. Now, in the next slides, I'd like to look at the time from the mid-Cretaceous onto the present day and down here in California and Mexico. And so there are a lot of questions about what happened between the mid-Cretaceous to present along California and Mexico. There are some thoughts that a conjugate Shatsky rise could have subducted and produced a flat slab. There are other hypotheses that suggest that there's both a Shatsky and a Hess conjugate that subducted under North America. Another hypothesis is that there was actually only a Hess conjugate that subducted. And then finally, it's been proposed recently that actually there may not have been a Shatsky conjugate, that there was a minimal or no Shatsky conjugate. And so I'd like to spend a little bit of time talking about this and showing some work on this topic. So first of all, one of the best places to look for places where we can see LIPs formed along a spreading bridge and involving a plume is the East Pacific rise. And here in this example, we can see where we have this Easter Island hotspot, that we have a conjugate on both sides. We have, now they don't look exactly the same, but what we don't see is that is a hotspot track on one side and nothing on the other side. And so the first point I want to make here is that um, when we look globally and we can see both sides of a plate of a spreading ridge, we don't. It's very difficult, or I don't think we can actually find any examples where we have a plume-driven large LIP eruption and we don't see a hotspot track on both conjugates. And some examples include the East Pacific Rise, Iceland, Kerguelen. Another example right here is the Galapagos hotspot. And here you can see again that they don't look exactly the same, but we can see LIP type of material, or buoyant material on both sides of the spreading ridge. And so importantly as well, in the East Pacific Rise, it looks like these plume-driven areas often show asymmetric spreading. And so I want to look at the Central Pacific and relook at the Shatsky and Hess rises, because some recent work has been done in these areas. And so just in the slide before, we looked at this Pacific Nazca system where we can see both sides across the spreading ridge. Now, up here, as we look into the Central Pacific, the other side, the Farallon side, has been subducted. And so we have to make guesses of what is on the other side. And so this is why we're looking more closely at this Pacific side. And when we look at the Shatsky and Hess rises, the Shatsky rise is over here. It's a bathymetric high in the Pacific, and it formed in the early Cretaceous. And then we have the Hess rise over here, which formed at a younger age. Important to looking at this area is the recognition that we have the Hawaiian Emperor Seamount chain cutting right in between. And so there's been some alterations to this area after the Hess and Shatsky rise formed. Some other features that are important are this slightly elevated area known as the Papanan Ridge and the Ojin Seamounts. And I'm going to show in a moment that some recent work suggests that the Ojin Seamounts is a hotspot track that connects the Shatsky and Hess rises, forming an integrated system. Another feature that I want to just point out here, because I'm going to mention it later, are the Mid-Pacific Mountains. And here, the Wentworth chains and the Line Island chain. So the reason why I'm mentioning the Mid-Pacific Islands and Line Island is because this is supposed to be a second hotspot track that is being used to test a Shatsky, Hess, Ojin, Hess, and Wentworth hotspot track. And so this is the work done by Ed Klennett, PhD candidate at UT Austin. And it's previous models of the Shatsky rise suggested that it basically formed under fairly stable conditions, where we have the older part of the Shatsky rise, or the oldest seafloor ages, and then progressing to a young seafloor age, meaning that we could basically project a very simple conjugate for the Shatsky rise. However, more recent work suggests that there were a number of ridge jumps that formed. And so here we can see going from old to young, and then old to young is reversed on this side. Then we have old to young and old to young. So basically, it's a much more complicated system. And what Ed has done is he's shown that modeling of ridge jumps, it still produces a sizable Shatsky conjugate. It's not as big as the Shatsky that we see today. It's about 40% shorter, but it's still sizable. And if we put this into a plate reconstruction, this shortened Shatsky conjugate would arrive along North America around 80 million years ago, assuming straightforward plate tectonic assumptions. Now, looking at some of the recent work for the Shatsky rise and Hess rise, there are two possible connections between the Shatsky rise and the Hess rise. The first is this Papanan Ridge, and the second is this more southerly connection along the Ojin Seamounts. Now, some of this more recent work indicates that the Shatsky and Hess rises, they both show isotopic similarities. And we can also see, there are also new argon-argon dates that show an age progression from 145 to 110. And so what Torsvik 2019 did is they tested different connections between the Shatsky and Hess rise in terms of the age progressive magnetism. And so this is the simplest model where the Shatsky and Hess rise are simply connected by a very direct hotspot track. And so what they found was that this produced mismatches to the mid-Pacific Mountains. In model B, and this was their preferred model, if the Shatsky and Hess rises were connected by the Ojin seamounts, they produced a hotspot track that would also fit well with the mid-Pacific Mountains. And the third model that, again, was not preferred was a Shatsky-Papana and Hess connection that goes very far to the north and then back down to the south. And so this work suggested that the Shatsky-Ojin-Hess connection produces the best fit. Now, there's been recent work that has dredged the Ojin seamounts, and these found new argon-argon ages that gives a nice age progression of magnetism along from the Shatsky into the Hess rise. And then these new dredge sites, it confirms a plume geochemistry in the area. So importantly, the Ojin seamounts are now thought to be a hotspot track that would have connected the Shatsky rise to the Hess rise. However, the Ojin seamounts seem to have formed off of the ridge. And so there are some questions about whether because it's not forming right at the ridge, it could have formed to the side. Are there conjugate Ojin seamounts on the Farallon plate? And so in this, in the next few slides, I'm going to show a model of the conjugate Ojin seamounts showing waning. So these originally would have formed at the ridge, and then we have waning magnetism, and then the Hess rise then forms afterwards. And so this is a method slide, a lot of words on this, but what I want to say is that I'm going to show in the next couple slides a model where we have plume ridge driven Farallon Pacific spreading. It's asymmetric, and the Shatsky conjugate is going to come into southern Sierra Nevada and northern Mojave at 90 million years ago, after Humphreys et al., which is in revision. And so this is an assumption that I need to make because there are a number of different unknowns in how to bring the Shatsky to North America. And so our rationale for bringing the Shatsky into this area is that around 85 to 90 million years ago, we see what looks like a lot of denudation. We see schist complexes forming and low angle faults. For the sake of time, I'm going to move past this slide because some of you are familiar with some of the constraints. But there is basically a narrow corridor between the northern Mojave and southern Sierra Nevada where a Shatsky conjugate presumably could have subducted, and we're going to assume that it does come into this area. And so, first of all, this is a movie showing the formation of the Shatsky conjugate and Hess conjugates in the Central Pacific at 145 million years ago. This red triangle is the hotspot location, and in blue you're going to see the Shatsky system. In orange will be the Hess, and in the middle will be the Ojin seamounts. And so as I play this movie, you can see the Shatsky conjugate forming. This is in a fixed Pacific reference frame. That went pretty fast, so I'm going to play that a couple of times. And so what you saw is the hotspot migrating in this reference frame, first forming the Shatsky conjugate, and then the Hess conjugate, and then this chain of seamounts. In between, are the Ojin seamounts over here. So I'm going to play this one more time. And first we can have a look at this at the Pacific plate, and then we'll have a look at the conjugates that form afterwards. So here again, we see the Shatsky forming. The hotspot is migrating. You can see that it's still located along this ridge. The Hess forms, and then the hotspot migrates and forms this line of seamounts. I'm going to play this one more time, and we're going to look at the conjugates that are predicted from this model. And here we can see this shortened Shatsky conjugate, the Ojin seamount track, which wanes and then picks back up. And then here is the Hess seamount, the Hess rise that forms. Now, if we go back in time, we can see that we don't predict any further conjugates because the ridge has now stepped away from the hotspot track. But back to the time of the formation of the Hess rise, there should be a conjugate because the hotspot is located very close to the ridge. And so we form this Hess conjugate. Now, what happens to this material as it moves towards North America? So what we've created here is a Shatsky conjugate. This is from Ed Clennett's work, and a Papanen rise conjugate. And here's the Ojin conjugate track that would have connected the Shatsky and Hess rises. And the final part of Hess forms around 110, 113 million years ago. And this entire system is 3,000 kilometers long. So here's a reconstruction showing both the Central Pacific and North America. In yellow here is California, and this is restored with the Klamaths restored and basin and range closed. Here's the insular in green. And I'm just going to play this a couple times, and we can have a look at where these conjugates end up. And remember that I have assumed that the Shatsky will end up in Southern California. And so we're looking for all the other conclusions that are produced apart from that. So I'm going to play that one more time, and this time with some narration. And so here's the hotspot. Shatsky is forming the Ojin seamount track. This is now approaching California. It's coming into Southern California at around 90 million years ago. And now we see this Ojin seamount track is subducting under northern Mexico. And here's the S conjugate that comes in and subducts in the early Cenozoic. So in the next slides, I'm going to just review some of the things that we produced in this model. So here we have imposed the Shatsky conjugate. We positioned it at the southern Sierra Nevadas because there's a range of places where this could end up, and this seems like a reasonable place. The total length of this conjugate system from the Shatsky all the way to the other side of the Hess is over 3,000 kilometers, so it's a very large chunk of real estate. By 85 million years ago, the Shatsky is fully subducted, and now we have the trailing Papanen and Ojin conjugates moving under or entering the subduction zone. By 75 million years ago, the Papanen conjugate is fully subducted, and now all we have left is this Ojin conjugate seamount track. And I've shown this kind of tapering out due to the waning as it moves away from the spreading ridge and then comes back to it. But we have a probable seamount track that is subducting under what could be southernmost California or northern Mexico. And these continue on to Arizona and New Mexico at this time. By 60 million years ago, this possible Ojin conjugate is now definitely subducting under Baja California. And this probably is starting to interact or continuing to interact with New Mexico. And then at around 55 million years ago, the Hess conjugate is subducting to the south, Baja California. And there's this corridor under Baja California, Arizona, and New Mexico where this material would be coming underneath the margin. And then by 50 million years ago, the Hess conjugate is fully subducted. And at this time, a number of things happen to the Farallon plate. The Farallon plate fragments into the Vancouver and Farallon plates. We know this from seafloor spreading anomalies that are still existing. And there's also a major Farallon plate motion change between 55 to 48 million years ago. And so if we go back to our example from the East Pacific rise, what we've just reconstructed is a conjugate system of two plume-related materials on an oceanic plate above a probable plume. And in the East Pacific rise, this is an area where we do see asymmetric spreading. And this plume actually adds viscous traction to help with this asymmetric spreading. And so some conclusions from this. First of all, one main point is that there are no known examples of a large plume-driven eruptions that don't have a conjugate plateau on the other side. Here's a preliminary plate model of a system that I'm calling SOCO for Shatsky, Ogin, Hess, and then CO for conjugate. I tried to present a conservative, realistic view of what could have subducted. And this is a 3,000 kilometer long area of plume-altered lithosphere that subducted between about 90 to 52 million years ago. And after about 75 million years ago, most of this material would have subducted south of Southern California. So I think I have maybe about 5 more minutes left. And so I want to just summarize some work that we're doing on copper porphyry systems under North America. And why are we looking at the Cordilleran region? Well, this is a map of critical mineral deposits, and you can see that this North American Cordilleran region has a significant concentration of critical minerals. And the work that I'm showing is a PhD thesis chapter that is being done by Maulud, who's working with me as a PhD student. I'm just going to play a small part of this plate reconstruction, but the main point here is that any plate reconstruction, if it's fully kinematic like this, has a lot of plate tectonic information that can be used to infer things about the Cordilleran region of Western North America. And whether you like this plate reconstruction or not, there's a lot of information that we can tap into for critical mineral systems, including porphyry copper systems. And so in terms of porphyry copper systems, we use this as a case study because it's generally agreed that there has to be some sort of plate tectonic link between porphyry copper deposits and plate tectonics. But the question is, what is the specific plate tectonic recipe? What is happening in the plate tectonic system to form these? And so here's just a little picture of maybe some of the cookie recipes that we have. We're trying to find the recipe to form porphyry copper systems. Now, this is a method slide, a lot of words, but all I want to focus here on is that we are using a supervised machine learning method. And what we put into this supervised machine learning method are two things. First is plate reconstruction. And I put in here red and multiple because we don't have an agreed plate tectonic reconstruction. And then training data. Where are the copper porphyry systems and where are some non-perspective areas? We can use a number of different machine learning algorithms, and then the outputs are a prediction map of where copper porphyries could be. Okay, and without going into the details, for those of you who are experienced with these types of plots, one factor that comes out is absolute plate convergence rates could potentially be in the copper porphyry recipe mix. And this is because, and this makes sense because if you're bringing more water into the subduction zone, you're probably increasing the amount of flux of volatiles. This is a reasonable expectation. And this is one example of a parameter that doesn't seem to be in the mix. This is ocean crust carbonate content. And this is probably not in the recipe and the reason is because when we try to predict positives, which are places where there are copper porphyry deposits, we find most of those areas are forming where we have 8% carbonate content in the oceanic crust based on models. However, the negatives are also forming at the same level. Here, the negatives are also forming at 8%. So there is really no predictive power in looking at this parameter. In contrast, when we look at absolute plate convergence, when we have higher plate convergence here around 13 centimeters per year, many of the copper porphyry systems are forming in this type of realm, whereas the negative, where we don't have copper porphyries, are forming at slower plate rates. And so I'm going to just move quickly through this because my time is limited. But here's a map from a previous study showing copper porphyry prediction. So here in red are areas that would be very prospective, and the black dots show actual copper porphyry systems, and this is broken down by time. Now, but one question for this is this plate model did not take into account any sort of terrain translations. And so if we look at the uncertainty that's created by that, and this is a plot of the same predictions, but this is paleolatitude, and this is time on this axis. The amount of uncertain area due to Baja BC type terrain translations would be within this box here. And you can see that a lot of the predictions are actually uncertain because Baja BC northward motions are not taken into account. And so I'm just going to fast forward and say that for the first time, as far as I'm aware, we've put two different plate tectonic models into this machine learning code to just try to see, could there be differences from the input plate model? And so here is a plate reconstruction that does not have terrain translations. And this is one that does have terrain translations. And when we put this into the porphyry copper supervised machine learning code, what we see immediately is that there are some significant differences here in the region between Arizona and Washington State. There are some places where we have high to moderate prospectivity and lower prospectivity in this plate model, whereas in this other plate model from Matthews without terrain translations, we have a different conclusion on prospectivity. And I'm not going to go into the overall differences, but this is just a hypothesis test showing that plate tectonics probably do need to be taken into account for these types of algorithms. And so just as a conclusion for this, for the first time, we've tested two possible Cordilleran plate reconstructions in machine learning code. That test took about a year to do, simply because of there's so much data that has to be systematically made consistent and thought about to put it into these codes. And there's also a need for more copper porphyry system training data, meaning that actual geologic data to train the system. But I'd like to, this is my second last slide. And I know that I went through things pretty quickly, and that's my fault for trying to fit in a lot of results in a short amount of time. But I'd like to talk about a possible way forward and a way that we could work together as a community. And this is to create what I call a geological plate reconstruction model to test in tomography. And the idea here is to take the magmatic record and any other geologic constraints and populate a North American plate model. This is East Asia, shown from the previous slide. But what we would have is a number of predictions of where subduction zones would be, and then test this against tomography. So can we find those slabs? For example, can we find the slabs for the Coast Mountains batholith or for the Sierra Nevadas in seismic tomography? Where would those be, and use those as markers? We could also compare it to paleomag. Both of these are independent from the model inputs. And so one question I have for everyone here is there interest to build a plate model like this using maybe our most confident geologic constraints to test against the mantle record. And so this is my last slide. Research is ongoing on how to use tomography for plate reconstructions. Today, you've seen two different hypotheses and two different outcomes for what we think about North American plate reconstructions back in time. If we look at the late Cretaceous to present day history, there's evidence that there would have been a Shatsky-Ogden-Hess conjugate subducted under California and northern Mexico, and with implications for Arizona and New Mexico. We're trying to test different plate reconstructions on machine learning algorithms. And then, as I highlighted in the previous slide, could there be interest in a community-led geologic plate reconstruction to test against tomography? So thank you, everybody.